Hey everyone, just another quick video to talk about Desmos 3D and how you can use that to look at tangent, normal, binormal vectors and what's called the osculating circle, which you can't see yet, but we'll get to in a minute. So you'll notice I have a curve. I'm just calling it C. Sometimes R is also commonly used. I'm just using C of t. Is this 2 times sine t cosine t 0.25 sine of at. That a you can adjust down here. So right now it's at 2. You can make that 3 or 4 or 5, and it'll make basically that sine in the z direction take on more turns. So you can have a much curvier circle in the z direction. X and y just being sine and cosine are pretty much just going to look like a circle going around in that direction, but looking with the z-axis, we can see that up and down from the sine curve. According to whatever that a value is, that's kind of going to adjust how many turns I'm going to have through there. So I'm going to put it back on 2. We'll adjust it again in a minute. But notice for all of these, I didn't have to really calculate it out for Desmos to display things. So this curvature formula, which we know can take a while to compute out, I'm just basically putting in this definition in terms of C, because I know my definition for C. So I have C prime cross C double prime, magnitude of that vector, whatever comes out, divided by this magnitude of C prime cubed. Curvature, right, there's many ways you can find it. This is just one of them, but it's one of the more useful in the fact that I don't have to define a bunch of other things. I can just use derivatives and second derivatives of C in that definition. The tangent vector is also here, which is C prime of t over C magnitude C prime. So we're basically taking the derivative, which is acceleration, but then normalizing it, right? Or I should say tangent C. The normal will be derivative tangent, so it's sort of the second derivative, but again normalized. So kind of like acceleration, but not really, because we're losing the length of that and just having direction. So that's what we're looking at in terms of t is just c prime over the magnitude, normal, right, t prime over the magnitude, and then this binormal vector is going to be t cross n. So tangent cross normal, that gives us this binormal vector, which is in purple down here. This is usually called the TNB frame, or the Frenet frame, sometimes referred to as that. And if I go ahead and adjust my n, you can kind of see how some of those vectors play out. You'll see that tangent vector in green, just tracing out the edge of the curve, kind of going in the direction of the edge of the curve at any particular time. You'll see the normal pointing basically toward the inside of the curve, maybe not directly toward the center, but somewhat toward the inside of the curve through that whole thing. And you'll see the binormal being the cross product of both of those. So if I go ahead and animate that, kind of see that t cross n. So again, follows the right hand rule, so that green cross red will point down in that purple direction right there. And because the tangent and the normal are both unit vectors, that binormal cross product will also be a unit vector, because this would form just a square of unit 1, and that would be the magnitude of that purple vector, so also unit 1. So that's what we're looking at for those. If you want to see a couple other things, I'll go ahead and show it. So this is the osculating plane. So osculating, osculate basically means to kiss, so that's the Latin, and the osculating plane is the plane that just touches, right, the curve at that one spot. So it includes the tangent. It also includes the normal, and the vector orthogonal to that plane will be that binormal vector. So because the word normal is already taken, then we call it binormal for that guy. So, so that is the vector, either normal or orthogonal, perpendicular, all those nice 90-degree words, right, to that plane. So that is the osculating plane. Now what we can also look at is something called the osculating circle. Um, One thing I'll point out before we get to that is this plane, right, is sort of the parametric equations with two variables to form that plane. So we basically have C of n, that's our green dot right there, green point, so that's kind of our starting point. And we're just going to move some number of units u in the t direction, some number of units v in the n direction. So, and I'm setting u to be -2 to 2, v -1 to 3. So that just takes us 2 in either direction along that green vector, both ways, and then -1 to the left in the direction of the red, or I should say opposite the red, 3 in the direction of the red. So you can kind of see how that plane is formed just by moving in the direction of each of those tangent and normal vectors. Again, right, I didn't have to compute it out. Desmos does all those calculations in the background, so that makes it kind of nice to be able to look at things without having to actually calculate the equations for them in terms of like sines, cosines, things like that. So just knowing the definitions is pretty helpful there. The osculating circle, so I'll go ahead and show that, is going to lie in the osculating plane. So I'm going to hide that plane in a minute, but just wanted to show you, right, this circle lies in that plane. That plane goes infinitely long, right, in every direction if you want it to. That circle is going to lie directly in that plane. So I'm going to go ahead and hide that just for display purposes. But this osculating circle is related to the curvature, right? So this is, instead of a tangent line, we have a tangent circle instead. And what you can do if you want to figure out, I'm going to pause this for a second. So if you want to figure out how to actually form that circle, right? Remember the osculating circle. The curvature of the curve is going to be basically 1 over the radius. And so the radius is also 1 over the curvature at that point. So we've already calculated curvature right up here. That was our k of t. And we'll just use that. So, so I'm putting a point at the center, right, of my circle. So this point at the center, so that's this dot. That's going to be my C of n. So I'm starting here at the green, C of n, and just going along the normal, right? So my normal vector length 1, I'm going to scale that by 1 over the curvature. And 1 over the curvature is the radius. So that takes me 1 radius length up to that center that's right there because I'm going in the direction of the normal vector. So that's what I get right there. So that's the center of the circle. If I want the edge, right, the edge around the circle, then again we could kind of think of this as just like when I formed the plane, right? I just traveled different directions to get points in the plane. What I'm going to do now is just travel kind of my sine cosine, right, forms a circle. So I need to go sine or cosine in the direction of that tangent, and sine or cosine in the direction of that normal vector that's right there. So that's what we're going to go ahead and try. So this is going to be my C of n, right? So that's this green dot right here. And then in the direction of tangent, right, I'm going basically this 1 over k, that's the radius, right? So the radius of my circle, cosine t, radius of my circle, sine t for the n. So that will just go all the way around the circle. This 1 over k times n, that's plus the c, that gives me my center. So center plus that radius times n, that puts me right here. And then I'm just adding from there different multiples of the sine t, cosine t times that tangent and normal. So just like other parametric equations, normally it's like r cosine t, but we have an I and jk direction. normally I and J. This time it's T and N. So we're just traveling in the direction of those T and N. This segment gives me kind of that line radius right there, just from one point to another. And then this is the shading down here. So that shading, again, I'm starting C of N plus that radius times the normal. So that takes me right there. And then this V is gonna, you can kind of see if I change this 0 to 1, gives me my shading, right? So V is how far out I'm going kind of as a radius from that center. So right now I'm only starting at 0.5 right there, going out to 1. So things radius 5 to radius 1 times this real radius 1 over k times that cosine. Again, the cosine and sine don't have anything to do with the original function. Those are just forming the circle, right? So sines and cosines put together for parametric equations will often give you those circles that go around. So cosine in the t direction, sine in the n direction, and then times that. V is a scaling factor of going from the radius out to the edge, and that 1 over k being the total radius from the center out to the edge of the circle. So that's kind of how you can do it in Desmos without necessarily having to calculate all these things, right? I didn't have to calculate curvature. I didn't have to calculate the tangent. Desmos is just going to display those as they are for any particular time that I might want to do on that n, right? And we can also see if I adjust that A, right, the more curvy I make this, the smaller those circles get, and then as we get to the bigger values, the bigger that circle gets. But around these more curved sections, we're just going to get those smaller circles right in there. Radius of the circle, remember, when that is small, that means curvature is high. So high curvature means smaller circle, because those radii and curvature values have the inverse relationship. All right, I think that'll do it for this one. Again, just a quick video to show you how you can code some things in Desmos if you want to visualize things that are going on, as long as you know your definitions and appropriate parametric equations, right? You can do pretty much anything you want. So, all right, that'll do it. I will see you on the next one.